When we think about computers, it's easy to picture a tiny magical brain tucked inside the machine, thinking through problems. But that isn't the reality. A microprocessor is more like a hyper-focused, extremely literal assistant sitting in an empty room, waiting for exact orders. This assistant has no common sense and no ability to guess what you want. It simply takes a card, performs the exact microtask written on it, grabs the next card, and repeats. To make sure there are absolutely no misunderstandings, the assistant only recognizes a rigid, pre-approved list of orders called an instruction set. For an early processor like the 8085, there are exactly 246 specific commands. If you give it a command outside that list, it simply stops working. We can actually see where this happens. This is an early microprocessor. If you look closely through the window on top, you can see the physical silicon die, the literal desk where our assistant sits, processing those rigid commands. Everything a computer does, from rendering a 3D video game to guiding a rocket into orbit, is built exclusively by stacking these tiny, simple, literal instructions on top of one another at lightning speed. Every order is a strict recipe card. It starts with an opcode, the core action, like chop. But actions need a target. You can't just chop, you must chop carrots. This target is the operand, the specific data the action applies to. Of course, the assistant is trapped in that empty room. To interact with us, it uses specialized mailboxes called I/O ports. It has inbox ports to fetch new data, like a keystroke from your keyboard, and outbox ports to push results away, like sending a pixel to your monitor. By forcing us to translate our complex human goals into these strict recipe cards, an action and a target, we create a reliable language that a completely blind machine can execute perfectly every time. To do any meaningful work, our assistant needs a place to keep its ingredients. This is the computer's memory. You can think of memory as a massive library where every single piece of data is stored in a specific slot with its own permanent identifying number, known as a memory address. Because this storage area is so vast, the assistant has developed a few different methods for tracking things down, which are called addressing modes. This diagram shows the simplest method, direct addressing. This is when the recipe card provides the exact coordinates of the data. The assistant walks directly to aisle 4, grabs the item, and goes right back to work. But sometimes the assistant uses indirect addressing. Here, the recipe card sends the assistant to a specific aisle, not to find a box, but to read a clipboard. That clipboard holds the actual address, and the assistant then bounces over to the true location to get the data. This method allows the processor to work through massive, constantly updating lists of data just by erasing and rewriting the location on the clipboard without ever having to print a new stack of recipe cards. When it's time to process that data, the assistant uses a personal scratchpad called the accumulator. All the manual math happens right here, one simple addition or subtraction at a time. Look what happens when a math problem gets too big. The scratchpad only has 8 slots. When two numbers add up to something larger than the space allows, the math spills over. This triggers a physical alert, a carry flag, which reminds the assistant to carry the one over to the next operation. Along with calculating totals, the assistant also compares conditions to make logical decisions. This diagram shows how the processor handles logic. It treats data like physical light switches. An AND command means the assistant checks 2 switches and only turns on the light if both are closed. An OR command means the light turns on if either switch is closed. Simple addition that sometimes overflows, and checking if switches are flipped on or off. These are the foundational building blocks of every complex decision a computer makes. If the assistant only ever read recipe cards in a straight, unyielding line, it wouldn't be very useful. To give software the ability to react, we use a mechanic called conditional jumps. It's like a choose-your-own-adventure book. The assistant checks a flag on the desk, and depending on what it says, skips ahead to a totally different page of instructions. We can see this on this historical printout of machine code. Notice the line JPNZ. That stands for jump if not 0. It tells the processor, if the scratch pad isn't 0, ignore the next card and jump up to the section labeled here. This skipping mechanism allows a video game to change when you press the jump button. Without branching, the game would play itself in a straight line. With it, the machine reacts to you. Now, suppose we need our literal assistant to perform a single chore 100 times. We certainly don't want to write out 100 identical recipe cards. Instead, we build a loop. This flowchart shows the 4 steps. First, write the number 100 on the scratch pad. Second, do the chore. Third, subtract 1 from the scratch pad. Finally, use a conditional jump to say, if the scratch pad is not 0, go back to step 2. This creates a self-sustaining cycle. The assistant keeps churning through the chore, crossing off numbers, until the exact moment the math results in a 0. The 0 flag pops up, the jump is canceled, and the assistant finally moves on to a new task. What makes this staggering is the scale. Even on a vintage 1970s processor, the assistant executes these loops roughly 3 million times every single second. Underneath every modern interface and AI model, there is no magic. There is only an obedient assistant, moving data, doing basic math, and turning pages at speeds the human mind can scarcely comprehend.